For our final chapter of electromagnetism, we are going to talk about electromagnetic induction. Electromagnetic induction is kind of the opposite of what we were talking about earlier, where we were talking about a magnetic field being caused by a current. Now we're talking about a current being caused by a magnetic field, and part of that is also going to explain how a magnetic field and an electric field are able to propagate as a wave in the first place, which is very important for the nature of light and the nature of electromagnetic waves as the propagation of electromagnetic radiation. Faraday and Henry both discovered that electric current can be produced in a wire simply by moving a magnet in or out of loops. No battery or other voltage source is needed, only the motion of a magnet in a wire loop. This phenomenon of inducing voltage by changing the magnetic field in loops of wire is called electromagnetic induction. When you place a magnet through a loop of wire, then it's going to cause there to be a voltage across it, which is going to cause there to be an electric field in turn. So a magnetic field or a change in the magnetic field going through a wire, a coil of wire, is going to cause there to be an electric field, which is going to be important later. If you increase the number of coils, then you increase the amount of voltage that occurs across the wire, the amount of current that's going through, and the strength of the electric field through the wire. So, this is something that only happens when you change the magnetic field that's going through it. If you just leave a magnet inside of an electric or inside of a coil, then it's not going to do anything. You have to change the magnetic field going through a coil or through a wire in order to change the current going through a wire. And this is also dependent on the area of the wire as well. So what it ends up being is the change of flux, which is the amount of the magnetic field going through an area. So a magnetic field times an area over time is going to cause there to be a voltage across the wire, which is going to cause there to be a current across the wire. Faraday's law states it better that the induced voltage in a coil is proportional to the product of its number of loops, the cross-sectional area of each loop, and the rate at which the magnetic field changes within these loops. This is very useful for creating generators which generate electricity. So by taking a loop of wire or a coil of wire and rotating it around magnetic field so that the magnetic field is going through the wire at some points and not through the wire at other points, it's going to cause there to be an alternating current that comes out because the current that comes out is dependent on the change in the field, the change in the flux going through the wire at different times. So this is the opposite of a motor. It is using mechanical energy to create an electrical output. So, two ways that we do this are with turbo generators and MHD, or magneto hydrodynamic generators. So, a turbo generator is just using steam from some source and putting it through an apparatus which is going to cause the wire to rotate around, which is going to cause there to be a generation of electricity, of alternating current. This is going to be most things that you're going to see because if you'll remember back in our energy section, most of the ways to generate energy basically just ended up generating steam in order to create mechanical or electrical energy. Another way is magnetohydrodynamic generator, which takes plasma itself, which you'll remember is a charged gas, an ionized gas, and forces it through a magnetic field so that the actual electrons are forced towards the top of the electrode and positive ions are forced towards the bottom of the electrode. And that's going to generate its own electricity directly through the injection of charged particles into a plate. Instead of making charges move in a magnetic field via a rotating armature, a plasma of electrons and positive ions expands through the nozzle and moves at supersonic speed through a magnetic field. Like the armature on the turbo generator, the motion of charges through the magnetic field gives rise to a voltage inflow of current in accordance with Faraday's law of induction. Whereas in a conventional generator, brushes carry this current to the external load circuit, in the MHD generator, the same function is performed by conducting plates or electrodes. Unlike the turbo generator, the MHD generator can operate at any temperature to which the plasma can be heated, either by combustion or by nuclear processes. The high temperature results in a high thermodynamic efficiency, which means more power for the same amount of fuel and less waste heat. Efficiency is further boosted when the waste heat is used to convert water into steam or to run a conventional steam turbine generator. Once the energy has been generated and the current is flowing through the electrical lines, we use transformers to change the voltage of the alternating current from the high voltage that you'll see in electrical lines to the relatively low voltage that you'll see running through your house. The way a transformer works is that it takes an AC current and creates a magnetic field in an iron core. This iron core is looped over another loop of coils, or another coil of loops, rather, in order to create a flux going through that coil of loop and induce a voltage in the same way that we've been talking about. Because the voltage induced is dependent on the number of coils, we can change the output voltage by changing the number of coils going in versus the number of coils going out. And because its AC current is constantly going to be changing, which means that it is constantly going to be creating a changing magnetic flux, which means that it's constantly going to be inducing another current, making it a sustainable solution instead of having to run a bar magnet in and out of a material or in and out of coils repeatedly like we did at the beginning of the chapter. So the primary voltage over the number of primary turns is equal to the secondary voltage over the number of secondary turns. So using this, we can take a high voltage from a power line and turn it to the 120 volts that we have in our home. Almost all electrical energy sold today is in the form of alternating current, traditionally because of the ease with which it can be transported from one voltage to another. Large currents in wires produce heat and energy losses, so power is transmitted great distances at high voltage and correspondingly low currents. Power is generated at 25,000 volts or less and is stepped up near the power station to as much as 750,000 volts for long distance transmission, then stepped down in stages at substations and distribution points to voltages used in industrial applications, often 440 volts or more, and for the home, 240 and 120 volts. As we've been talking about, a magnetic field causes there to be a voltage across a wire, which means that it can cause there to be an electric field as well. So an electric field is induced in any region of space in which a magnetic field is changing with time. And then Maxwell, in addition to Faraday's law, found that a magnetic field is induced in any region of space in which an electric field is changing with time. What this means is that if you have a magnetic field that is changing sinusoidally, that is going to cause there to be an electric field, which is going to change sinusoidally. And each of these fields is going to push the other one forward in the direction perpendicular to both of them. So there are two perpendicular fields, the magnetic field and the electric field, which oscillate up and down and which push each other forward as an electromagnetic wave, which is how we're able to get electromagnetic radiation and how we're able to survive thanks to the sun's rays.